Hello everyone, I am Siddharthan. Currently, we are in the eighth module of our hands-on machine learning course, and in this eighth module, we have discussed about the topics such as cross-validation, hyperparameter tuning, model selection, etc. And the next topic that we are going to move on is model evaluation. Model evaluation is one of the most important and basic tasks that we have to do in any machine learning use case. And the significance of this model evaluation is that it helps us to understand how accurate our model is and how is the performance of our model. So we try to quantify the performance of this model, and this is what we call as model evaluation. And the first topic in this model evaluation is accuracy score and confusion matrix. So in this video, let's try to understand what is meant by this accuracy score and what is meant by this confusion matrix and how we can implement this in Python. So this will be the agenda for today's video, and let's get started. So the first thing that we have to discuss here is the types of supervised learning. So we have discussed this like several times before in our machine learning course. So we know that we divide supervised learning into two kind of tasks. One is classification and regression. So a classification is a problem when we have to predict a particular class or a discrete value, whereas regression is about predicting a quantity or continuous value. Let's say that we are predicting whether a person is going to get a job or not. So this is like an yes or no question where yes is one class and no is another class. Whereas if you try to predict what is the salary that the person is going to get from that job, then it is called as a regression problem because we are predicting some numerical value, some quantifiable value. Whereas in the classification, we just try to classify the data points. So this is the difference between these two. The example of this classification is like predicting whether an object is red in color or green in color, or true or false, whether a person is having diabetes or not. So this is like example of classification problem, whereas predicting the salary of a person or age or predicting the price of a house or a car, so these comes under regression. Okay. And the model evaluation technique for classification problem, so one such example is accuracy score. Okay. And in the case of regression, we cannot use this accuracy score, so I'll explain you why we can't use that. And whereas in the case of regression, we use this error values like mean absolute error, mean squared error, etc. So we will discuss about this regression evaluation metrics later, but let's try to understand about this accuracy score. So how we are calculating this, and what is the limitation of this accuracy score and why we need this confusion metric. So these are the things that we will be discussing in this particular video. So I'll just start with the definition of this accuracy score. In classification problems, accuracy score is the ratio of number of correct predictions to the total number of input data points. Okay. So what we take here is like we need two values. One is the number of correct predictions made by the model. Okay. Divided by how many total data points are there for predictions. So let's say that we can consider the accuracy score formula something like this. So accuracy score is equal to we have to take this number of correct predictions. So we have to divide it by total number of data points, and so this value will be between 0 to 1. So like it will be 0.80 or 0.90. So if the accuracy score value is 0.95, that means the model is 95% accurate. In order to convert it to percentage, we can multiply it with 100. So the value will be in percentage. Okay. So let's try to understand this with an example. Let's say that the number of correct predictions made by the model in a case is 128. Okay. Let's say that we are building a machine learning model that can predict whether a person has diabetes or not. And so out of the test data that we are going to predict, the model is making correct predictions for 128, and the total number of data points that we have is 150. Okay. So we are checking 150 people based on like some factors like what is their age, what is their gender, and so on. So that let's say that there are like these factors, and based on these factors we have to determine whether that person is diabetic or not. So we are checking this for 150 data points, or you can consider this as 150 different people. Out of this 150 different people, let's say that the model has predicted correctly for 128 people or 128 data points. So you just have to plug in these values. So number of correct predictions is 128, and the total number of data points for which we are predicting is 150. So we just have to divide it, and when you divide 128 by 150, this is the value that you get. So 128 by 150 is equal to 0.853, and when you multiply it with 100, you will get 85.3 percentage. So the accuracy score of your model is 85 percentage. What does this 85 percentage means is, if you using this model, if you try to predict for 100 data points, you will get correct predictions for 85 data points. So this is what accuracy score means, generally speaking. So there is not a thumb rule, but we can say that if the accuracy score of the model is like greater than 80%, then it is like a decent performing model. If the accuracy score is like greater than 90 or 95, then it is like a very good model that can make like accurate predictions. So we can import this accuracy score from this sklearn module called as sklearn.metrics. So I'll show you in code as well how we can do this, but you can remember that we can import this from sklearn.metrics input accuracy score, and I'm sure that most of you might already know this. So like there is one limitation of this accuracy score. So we have discussed all these things, and we have no like we have seen that this is how we can quantify the performance of the model, but there is like one significant limitation to this accuracy score. So accuracy score is not reliable when the data set has an uneven distribution of classes. So this is very important. Let's say that we are training our model to predict whether a person has heart disease or not. So this is again two classes: person with heart disease, person without heart disease. Let's say that the total size of the data set is like 1,000. If there is like uneven distribution, in that case accuracy score can be misleading. Okay, so we cannot rely on accuracy score. Let's try to understand this with an example. So let's say that we are building some deep neural network in order to predict whether an image represents either a dog or a cat. Okay, and the total number of images we have in the original data set are 800 dog images and 200 cat images. Okay, as we can see here, there are two classes. First class is dog and the second class is cat. Here, as I've told you, there is a very high uneven distribution of classes. So it is like 4:1 ratio of dog images to cat images, and like the dog images is the number of dog images is very high compared to the cat images. When we have a data set like this, if we train our neural network or any machine learning model with this kind of data, the machine learning model cannot understand the difference between a dog image and a cat image, just because the number of images for one class is very high. So what happens is it will predict all the images as dog. It won't predict any cat images as cat. So this is the problem with uneven distribution of data. So let's say that the number of images predicted as dog is 1,000. So we have, let's say that we have trained our neural network with this 1,000 images, and we are like again predicting. Using this neural network, we are predicting with the training data. Let's say this is our training data, which is 800 dog images and 200 cat images. As I've told you, as there are there is like insufficient amount of cat images, all the images will be predicted as a dog. So there is a possibility for this. So let's say that out of 1,000, all the images has been predicted as dog. If you calculate the accuracy score in this case, let's see what is the value that we are getting. So the number of images predicted as cat is 0, obviously, because all the images are predicted as dog. So the number of correct predictions in this case is 800, right? Because obviously, so out of these 1,000 images, 800 are dog images. So we will consider these as correct predictions. Whereas the total number of data points in this case is 1,000. So if you want to find the accuracy score, we will divide it by 800 divided by 1,000 into 100%. So this is what we have seen before. Number of correct predictions divided by total number of data points, and this is what we get. 800 divided by 1,000 into 100. So the final accuracy score that you get is 80%. Okay, right? So we can say that 80% is a good accuracy score, right? But this is not a good performing model. So this is actually an underperforming model. Let's try to understand why. So we are going to use this trained model that has been trained on uneven distribution of dog images and cat images. And now let's say that we have a different test data. And in this test data, there are 200 dog images and 200 cat images, right? And the model hasn't seen these images before. So when you use that model, which is trained on an uneven distributed data set, if you use that particular model, again, all the images will be classified as dog because the model doesn't understand how a cat image looks like. So out of these like 400 images, so there are like 200 dog images and 200 cat images. All the images will be predicted as dog by our machine learning model, and no images will be predicted as cat. So in this case, the total number of correct predictions is 200, and the total number of data points is 400, right? Because out of these 400, 200 are dog. So 200 are obviously correct, and the remaining 200 are wrong, right? So the total number of correct predictions is 200, and total number of data points is 400. In this case, if we try to find the accuracy score, it is correct predictions by total number of data points, which is 200 by 400. In this case, the accuracy score is 50%. So there is like a huge difference between this accuracy score, which is 80%, and this accuracy score. So this is why accuracy score is not reliable when there is an uneven distribution of data. Okay, so if there is like let's say that in the training data there are like an uneven distribution, in that case we may get an high accuracy score, but it is actually a wrong score because all the images are predicted as cat. So we can say that the model is not performing well. and we can capture this incorrect performance of the model when only like when we have a data set like this where the distribution is kind of even. So this is where the metrics like confusion matrix or precision and recall comes into play. So in this video, let's try to understand how confusion matrix kind of helps us in order to understand this this limitation of this accuracy score and how we can use that efficiently. In the next video, I'll explain you about this precision and recall and all those things. So let's discuss about this confusion matrix now. So confusion matrix is a matrix used for evaluating the performance of a classification model. So again, we can use this only for classification model, and it gives more information than the accuracy score. So like let's say what is that particular information that is helpful for us. Let's say that this is the true class of the data points, so positive and negative, and this is the predicted class. So in this case, the previous case, the two classes are dog and cat. So in this case, we are considering as positive and negative as the two classes that we have. So this is the true class, so true labels, and this is the value predicted by our model. Let's say that we are doing this for COVID-19 test cases. So let's say that there is some test like RT-PCR or this rapid antigen test. So we have these two tests for COVID-19. Let's say that uh, we have this true class and predicted class. So true class is whether a person is really having this COVID-19 infection, and predicted class is, let's say, the values predicted by our model. So let's say that we are building a ML model that can predict whether a person has COVID-19 infection or not based on certain symptoms. So let's consider this. So the first quadrant of this confusion matrix represents my true positive. So what does this true positive means is, so the true class of the person is positive. That means a person actually has a COVID-19 infection, and the model also predicted correctly. So you have to see this label and this label. So this is my true class and this is my predicted class. So both these things matches, right? So we can say that this is my correct prediction. So what this basically means is a person really has COVID-19 infection and the model has also predicted correctly. And what does the second box represent is true class is negative. That means a person doesn't have any COVID-19 infection, but the model has predicted that that person has COVID-19 infection. So this is what we call as false positive, because this positive is not correct one. So this is an incorrect one. Whereas we call this as true positive, which is represented as TP because the person is actually positive. And the third quadrant in this case is false negative. So in this case, the true class is positive, which means a person has COVID-19 infection, but they have been predicted as negative. So this is what we call as false negative, and the final quadrant is true negative. So the person doesn't have COVID-19 infection, so they are like really negative, but the model has also, so the model also predicted as negative. So this is what we call as true negative. So these two green color boxes represent my correct predictions, and these two red color boxes represent my wrong predictions. So true prediction is nothing but, so TP means when a person is tested positive for COVID-19 and the model also predicted correctly that they have infection, so it is called as true positive. And what is meant by this true negative is that a person doesn't have COVID-19 infection and the model has also predicted correctly that they are negative for COVID-19 infection. So these two are my correct predictions. And false positive is something when a person doesn't have any infection. So we have this true class is negative, but the model has predicted it as positive. So we have this as false positive. And finally, we have this false negative, which means like a person actually has the infection, but the model has predicted that the person doesn't have any infection. So TP plus TN count represents my correct predictions. Okay, true positive and true negative represent my correct prediction, and false positive and false negative represent my wrong predictions. And you can use this sklearn.metrics.confusion matrix in order to use this confusion matrix. We will also discuss how we can implement this in Python. And again, so this is a very important concept that you have to understand. So there will definitely be questions on this particular topic in most of the machine learning and data science interview that you attend. Okay, so the easiest way to understand is by through this COVID-19 infections or any other this medical condition, because like there is like a true positive and false positive, false negative and true negative cases. Like these terms are used in the clinical field as well. So this is how like they kind of represent people who have been tested positive if they are if they don't have any infection and things like that. So this is an actual term that is used in the clinical field, and this is what we use in confusion matrix as well. So the advantage of this confusion matrix is, even like when there is this uneven distribution of classes, even though there is like this I accuracy score. So in this case, we know that the accuracy score is I. But when you implement a confusion matrix in such cases, we can clearly see whether the model is making good predictions, or whether all the models has been predicted as one class. So this is how confusion matrix will be helpful for us. And now let's try to understand how we can kind of implement this in Python. Okay. So I'll open my Google Colab. So I have this code ready already. So the data set in this case that I've used is this art disease prediction that we have used before. I'll also give the link for this video where I've completely explained you how you can use this data set in order to predict whether a person has this art disease or not. So I'm not going to go into all these details. Let's directly come to this model evaluation part. So we have processed this data set, splitted it into training data and test data, and we have trained our logistic regression model with this X-train and Y-train. Okay, so this is my model evaluation part, and I'm going to calculate my accuracy score. So I'm importing my accuracy score function from sklearn.metrics. Okay, and I'm creating a variable called as X-train prediction, and I'm going to predict the values. So model is my logistic regression model, which is trained on the training data, and I'm predicting the labels for my training data. Okay, so X-train prediction is equal to model.predict. So I'm storing all the predicted labels in this X-train prediction. Okay, and I'm going to calculate the accuracy score. So that accuracy score is stored in the variable called as training data accuracy. So I'm using this accuracy score function, and within this I have to mention the true label and the predicted label. In this case, the true label is Y train, which we have obtained from this train test split. So here your Y train, okay, which is my training data prediction, and the prediction made by the model, which is X train prediction. So accuracy score will compare these two set of arrays, and it will give us the accuracy score. So in this, if I print this accuracy score, the value is 0.8553, which is equal to 85.53 percentage. And if you want to round this to percentage, you can use this round. So round will kind of it is used to remove some decimal places, or it can also convert like floating point value into integers. So it will basically round the values. So what I'm doing here is I wanted to round this training data accuracy, which is in this range of like 0.85 or something. So I'm going to multiply it with 100 in order to convert it to percentage. What does this 2 represent is I want two decimal places. I want two decimal values. So if you want like three decimal values, in this case, we have to mention three. So this has been rounded. So it is like 85537. So this 3 has been rounded to 4, as we have the value as 7 in this case, and we are adding a percentage symbol to it. So as you can see in this case, the accuracy score value is 85.54 percentage, which means if you predict for using this model, if you predict whether a person is having heart disease or not for 100 people, 100 data points, the model can make correct prediction for 85 people. So this is what we call as an accuracy score. So this is the accuracy score on the training data. And this I'm just doing the same thing. The only difference is that I'm calculating the accuracy score for test data. And this accuracy score is like very important. The training data accuracy is not that important, but test data accuracy is very important. So I'm calling my X-test prediction, where I'm storing all the predictions made by the model, and I'm storing this to X-test prediction, and I'm using this accuracy score function. So Y-test comma X-test prediction. So I'm comparing the true test labels and the labels predicted by my model using this accuracy score function, and the accuracy score is 80.32 percentage. So when I round this to two decimal places, I'm getting the percentage value as 80.33 percentage. So I'm sure that most of you would know this already, calculating this accuracy score. Now let's move on to confusion matrix in order to understand that how we can represent that matrix using this confusion matrix. So from sklearn.metrics, I'm importing confusion matrix. So this is the function in order to calculate this, and I'm creating a variable called a CF matrix. So CF matrix, confusion matrix of Y test and X test prediction. So it is just similar to this step. So instead of using accuracy score, we are using this confusion matrix function, and we are storing this matrix to CF matrix. So as you can see, the result is stored in a matrix. That's why we are naming this as confusion matrix. I'm creating a variable as a short form of CF matrix, and I'm printing it. So this is the value that I'm getting, 22, 6, 6, 27. But we are not sure what does these values means, right? Like in this case, we have two labels. So the first label is 1. 1 means a person is having heart disease. 0 means a person doesn't have heart disease. Okay. But in this case, we are not sure. Like what does this 22 means, 6 or 27 means. So we are not sure which is true positive or which is false negative, and so on. You can go to this sklearn.metrics.confusion matrix documentation in sklearn, you can see the order here. So in the case of binary cases is when you have like two classes. In this case, we have two classes as person with R disease and person without R disease, right? So this is the order. First is true negative, and then we have false positive, false negative, and true positive. So these are like the order that we have, and you can kind of get this values using this dot travel function. So I'm going to like extract these values using the CF matrix dot travel. CF matrix is where I have stored my confusion matrix, and we will get all this true negative value, false positive value, false negative value, and true positive value. So this is how you can extract all these values. And also the other important thing is you can also build this confusion matrix for multi-class classification problem. If you see in this one, they have like multiple classes: ant, bird, and cat, whereas in this case we have only two classes. So you can also use this confusion matrix for multi-class classification problems as well. And if you are not sure on what does this number represents, and if you want to represent this in an heat map, that is also possible. And it is like a more efficient way in order to understand this confusion matrix. So it is like similar to how we have built this confusion matrix here. So you can import this Seaborn library, as we know that this is a data visualization library, and we are going to load this confusion matrix in the form of a heat map. Okay, so I'm calling this sns.heatmap function, and the parameter I'm passing is my confusion matrix, and annotation is equal to true. So like I want these values, so label values. So that's what this annotation means. Now let's see what does this confusion matrix, this particular heat map represents. So we have the value 0. Here also we have the value 0. So this means my true prediction. So you can just see this label in the y-axis and the label in the x-axis. If both the things match, that is my correct predictions. So in this case 0, let's say that this is my true class, okay, true label, and this is my predicted label. So in this case, what does this 22 means is like 22 data points as the label 0, and all those 22 data points has been classified as 0. And this 27 means is like those 27 data points as the label 1, and they have been predicted as the label 1. So these are my correct predictions. So these are the green colored boxes represented here. So you just have to see the label in both the sides. Here it is positive, where it is also positive. So we have like green color here, which is the correct prediction. So in this case we have positive and negative, so there is like a mismatch in the classes that we have in this case. So this is a wrong prediction. In this case, if you see in this third quadrant, we have negative and positive, so it is a wrong prediction. So here if you see this is negative and this is also negative, so this is a true prediction. So that is the idea here. So here we have the value as 0 in the x-axis for this quadrant. The here also the value is 0. So this represents, this 22 represents my correct prediction. And in this case 1 represents like here we have 1, here also we have 1. So 27 is my correct prediction, and the 6 and 6 are my wrong prediction. So what this means is like 6 people who so let me go to the 0. Let's try to understand what this 0 means. So 0 is LTR means a person doesn't have R disease, right? So this 6 means 6 people doesn't have R disease, but they have been predicted as 1. So if you see this quadrant, you have to just see the horizontal label and the vertical label. So if you go here, this is my 0 and this is my 1. So there is a mismatch. So people doesn't have R disease has been predicted as people with R disease. So there are like 6 wrong predictions in this case. And in this case, like people do have R disease, so we have the label 1, and they have been predicted that they don't have R disease. So these two represent my wrong prediction. So you just have to see the labels in the y-axis as well as the x-axis, and you will know which are the correct predictions. So when there is like a problem like this, so we have seen, right? So when we have a problem like this, when there is a chance that the data is undistributed, even though the accuracy score is kind of high, you can try to build this confusion matrix and heat map to understand whether the model is making good prediction, or all the values has been predicted into only one labels. Okay, so that is the importance of this confusion matrix. So in that case, the model will be predicting like only 0 will be predicted in both the cases. No prediction will be made for the class 1. So that is what happens for this uneven distributed data, and that is where we use this confusion matrix. And again, we have also metrics like precisions and recall, which we will discuss in the upcoming video. So this is for only binary classification problem, right? You can also again use this for multi-class classification also, when we have like more than 2 labels. And I have another example for you, and I'll share this Google Colab file link in the description of this video. You can check that out. I have given a link of a Colab file, which is again an example for multi-class classification problem. So we have already worked on this in our channel. So this is the MNIST and written digit classification using neural network. I'll also give the link for this video in the description as well. So we have worked on this. So here we are predicting whether an image, like what is the digit represented in the image. So the images that we are considering, ranges from 0 to 9, whether it is 0 or 1 or 2, all the way up to 9. So this is what we are predicting. And here also we can build this confusion matrix. So here, so this is the accuracy on the training data, which is 90, like 0.989, which means like 98.9 percentage. So this is my training data accuracy, and you can get this test data accuracy using this evaluate function when it is deep learning problem. Okay, so this is when we use sklearn models. This is when we use like neural network from Keras and TensorFlow. So here we are building this neural network using this, sequential from Keras. So let me just open this. So yeah, so we are building a neural network here using Keras, and when you do that, there is a function called as evaluate, and this will calculate my test data accuracy. And in this case, the test data accuracy is 97.1 percentage. So this doesn't give any more information. So we can know that out of 100 values, the model can predict correct values for 97 data points, right? So now let's try to understand how can we build this confusion matrix. So yeah, so this is my confusion matrix, function that we are importing. So let me just go to this one. So yeah, so from TensorFlow.math. So we don't have to import this from sklearn.metrics. So this is we are importing the confusion matrix from sklearn.metrics. We also have this function in TensorFlow as well. So TensorFlow.math has this function called as confusion matrix, but the function is the same. So in both the cases, the function is same. In this case, as we are working with Keras and TensorFlow, we are importing the confusion matrix from TensorFlow. So I'm creating a variable called as confusion. So CAONF mat, which is my confusion matrix, and I'm passing my y test and y pred labels. So y test is my true test data labels, and y pred labels is the label predicted by my model. If I print my confusion matrix, this is the value that I'm getting. So in this case, this won't make any sense. And now we can pass this confusion matrix to an heat map in order to understand this better. So here I'm building a heat map. So plt.figure, where I'm setting the size of this plot, and I'm saying sns.heatmap. So I'm constructing an heat map with this confusion matrix. So I'm just mentioning that annotation is equal to true. So fmt is equal to d means I want all the values in the form of integers. So I don't want any values in floating point values. CMap blues. So I'm just setting the color of this heat map. So PLT y label and x label. So I'm going to set the true labels as my y axis and predicted labels as my x axis. Now let's try to understand how we can infer this. So this is actually the same data that we have here. So instead of having this in numerical values, we are constructing a heat map. Now let's try to understand what does this signifies. I told you, right, when the two classes match. So in this case, so we have positive and positive. That means the predictions are correct predictions. So in this case, we have negative here and negative here. So this is my true predictions. So in this case, positive and negative. So there is a mismatch in the class in this red color quadrant, in this red color quadrant. So you have to check whether the classes are matching. So this diagonal thing, so all the values in the diagonal represent my correct prediction, because if you see the corresponding labels here for this first quadrant, the y-axis value is 0. If you just come to this x-axis label, it is 0. So this is my true label, this is my predicted label. So what does this 969 represent is, if you go to this y-test prediction, so let me go here. So x test dot shape. So this is the pixel size of the image. So it is like a 28 into 28 image, and the total number of test data points that we have is 10,000. Okay. So in this case, the training data, let's see, uh, the number of training data that we have here, I think is 10,000. Yeah. Yeah, as you can see, so this is the white train shape, white test shape. So totally we have 60,000 training data images, which are like 60,000 images of numbers, and 10,000 test images. So the totally there are like 10,000 test images, and out of those 10,000 images, 969 images have the label 0. That means that image represents 0, and this 969 images has been correctly predicted as 0. So that is what we have here. So you have to see the y-axis label and the x-axis label. Consider this as x-axis and consider this as y-axis. So 969 images represent 0, and those has been predicted correctly as 0. So there is a match of class. If you see the next quadrant value, it is 1. That means one image and the true label of this image is 0 has been predicted as 1. So what does this signifies is, an image that has the image of 0 has been predicted as 1, and in this case 1 again. So in this case, only one image which is actually 0 has been predicted as 2. So that is what these values represent. If you see this 3, so 3 images which actually represent 0 has been predicted as 8. So this is how you can infer this confusion matrix. So if you see this 1122, so 1122 values represent the image 1, and they have been correctly predicted as 1. So if you see this 4 images of 1 has been predicted as 8, and so on. So if you see which has the highest value, 24. So what does this 24 means is the true label for these 24 images are 9, but they have been predicted as 4. So you can just understand, like 9 and 4 may kind of look similar to the model, as you know these are like handwritten images. So these 24 images has been wrongly predicted as 4. So 9, like 24 images of 9 has been predicted as 4. So whereas if you consider this one, so there is 9 here and there is 9 here, so there is match of class. So this is how you can infer a confusion matrix in the case of a multi-class classification problem. And it is always better to load this confusion matrix into an heat map to understand it better. So if there is a match of class, then in that case it represent correct prediction. If there is like mismatch, that it represents wrong prediction. Or the other thing that you can understand is this diagonal represents my correct prediction, all the other values represent my wrong prediction. So here also this diagonal represent my correct prediction because we have match of class 0 and 0, 1 and 1. So for this, so similarly we have the 0 and 0 here, 1 and 1 here. So this diagonal represent my correct prediction. So this is how uh, we kind of use this confusion matrix in order to understand, like we kind of like understand the performance of the model better. Whereas in the case of accuracy score, it will just tell you that 97 percentage. So out of 100 images, 97 images will be predicted correctly, and for 1000 images, 970 images will be predicted correctly. So this is what this accuracy score means. Whereas if you build this confusion matrix, it will tell you what images are being predicted as what. So if you see this one, 23 images of 3 has been wrongly predicted as 5. So this is some information which accuracy score won't tell you. So this is why confusion matrix is very important for us, and like we can infer a lot from it. So that's it from my side, and I hope that you understand all the things that we have covered in this video about accuracy score and confusion matrix. So yeah, that's it from my side, and I'll see you in the next upload. Thanks for watching.